In this section, we're going to look at using vectors to solve kinematics problems in the context of a boat travelling across a river which also has a water flow. So here we have a boat that is rowing from point A on one bank of the river in a perpendicular direction to point B on the other side. The boat is being rowed at a constant speed of 4.1 metres per second. Sometimes questions will say the speed is 4.1 metres per second relative to the water. What this means is this is the speed of the boat assuming that the water is not moving it as well. The river is flowing in a direction parallel to the riverbank. The river is flowing at a speed of 2 metres per second. We can show these two velocities as vectors. So we can see the velocity of the boat is here and the velocity of the river is here. We're using a single arrowhead to show these velocities. We want to consider where the boat will end up. Now, because the boat is trying to travel straight across the river, but it is being swept along by the currents, it will actually end up further downstream. We want to know what angle the boat approached the opposite riverbank. In order to combine these two velocities together, we can take the vector which represents the velocity of the boat and the vector that represents the velocity of the water, and we can put them head to tail. What this means is that the front end of one vector is then at the back end of the second vector. This wouldn't work if we put them head to head or tail to tail, so be careful that you have, at the point where the vectors join, you have one going in and then one coming out. We can then put the resultant velocity, which is the final direction that the boat ends up travelling in, as the third side of the triangle. Now, to show that this is the resultant velocity, we use two arrows instead of one. You can see that we start at the tail end of the first vector and travel directly to the head end of the second vector for this resultant velocity. Because we have a right angled triangle here and we've got two of the sides, we can use trigonometry to find the angle. We have got the opposite and the adjacent side, so we can use tan theta here. Tan theta would be 4.1 over 2, which leads us to an angle of theta is 64 degrees. This means that the boat approaches the opposite riverbank at an angle of 64 degrees. Suppose the width of the river is 65 metres. We want to know how far the boat ends up away from B. So in other words, if we know this width here, we want to know this distance here. The vector diagram will be the same for the velocity as it is for displacements. So we can use the same angle. However, we can't mix and match the values that we put on the side lengths. So if we are using velocities, then all of the sides need to be a velocity. If we are calculating for displacements, all of the sides need to be a displacement. We can't have one side representing a velocity and another side representing a displacement. So we can put 65 along this side here, and we are trying to find this length here. We now have a right angle triangle where we know one side and one angle, so again we can use trigonometry to give us that tan 64 would be 65 over x, and rearranging this to solve gives us x is 31.7 metres. So this is the distance that the boat has drifted along the river. Suppose now the boat needs to return to point A. So turning around, we now need to travel back. Consider which direction the boat would need to travel in order to ensure that it did actually arrive at point A. It's going to travel at the same speed of 4.1 meters per second. However, if the boat just sets off in the direction of A, because of the impact of the water, it will actually end up further along to the right. So in order for it to arrive at point A, it actually needs to travel in a direction that is further up the riverbank. So the boat's going to aim past A, and the flow of the river is going to push it back. So this time, the 4.1 meters per second, which is the velocity of the boat, will be in this direction here. We then put the vector of the velocity of the boat head to tail with the velocity, the vector for the velocity of the water. As you can see, we have the head of this vector meeting the tail of this vector. We can then put the resultant velocity here with two arrows going from the tail of the first vector straight to the head of the second. Now this is not a right angle triangle, so for this we either need to use the sine rule or the cosine rule, and in this case we can see it will be the sine rule. We know that this angle here is 64 degrees. This is because we have parallel lines for the banks of the river, and here we have an alternate angle, or a Z angle, and we previously calculated that this angle here was 64, so we have 64 over here. From that we can calculate this inside angle. 180 minus 64 gives us this angle of 116. We can now use the sine rule as we have two pairs of angles opposite sides. Here we have sine theta over 2 equals sine 116 over 4.1. We can then rearrange this to give us theta equals 26 degrees. However, this is not the final answer, as we do need to know what angle the boat makes with the riverbank. So because we know that the angle here that we calculated earlier is 64, and we've just calculated this angle here as being 26, if we find 64 take away 26, this will give us the angle that we want, which is the angle between the riverbank and the direction that the boat is rowing in. Remember that this is not the direction that the boat is actually travelling in the end. This is the direction the boat is trying to move in, but because it's being pushed back by the water, it will actually end up travelling at an angle of 64. Now have a go at these two questions on page 130, exercise 3.2. They are question 1 and question 3.